everybody does it at the same time, then it means that you and all the people you love are seeing the same moon at the same time, and so you're connected. It's a beautiful tradition. So if you want some mooncakes, I have 3 of them. Eat your mooncakes and think of your loved ones. Today's your chance. Did I get that right, Kevin? Why am I? So can we get this screen off? Okay. All right. So let's begin. Today and in the next class, we're going to be looking at AdaBoost. We're sort of switching topics slightly from pure signal processing and machine learning techniques related to signal processing. We will link things back in the next class. In the next class, we will also present the projects. We have a choice of 3 projects for you guys to pick from. So we'll present these to you. We picked some things that we think are fun, but then whether they are fun or not will depend on how we do it. So, but first, this week, it's all about trying to detect faces in images. Now, we know from the last lecture how to describe a face. We started off with a typical face, which captured, in some sense, the essence of facehood. This was our, what was this? Our principal eigenface. And then every face in the world could be approximated as a scaled version of this image, and it will still look like a face. You get most of what was the most important thing of a face image, that it is a face. And so if I had many such eigenfaces, many such typical faces, then each of them captured detail that the previous one did not. And so you could express each face as a weighted combination of all of these typical faces. And the more you added, the cleaner the reconstruction got. And if you use the eigen decomposition, then these typical faces were very face-like. They represented what looked like faces. In so doing, we introduce the notion of a typical face. Now I can use a typical face to construct faces. What else can I use it for? Store. Kidnap proof. But if I have a notion of what a face looks like, what can I do it? What can I use it for? I can detect faces in images, can I not? So because it tells me what faces are like. So we're going to be looking at detecting faces in images. I like to begin with this picture here. As an Indian, it's one of my favorite pictures. This is a famous conference in the 1930s, I think. And almost every single person in this picture got a Nobel Prize in physics. The one prominent person here who didn't get a Nobel Prize happened to be Indian. So the guy who discovered the boson. Anyway, suppose I wanted to detect all the faces in this image. How would I do it? A simple solution. I know what a typical face looks like. I can go looking for the typical faces in my image. So if I started, for instance, with this image here, this is a 400 cross 200 image. I have a notion of what a typical face looks like in a standard picture from Seinfeld. I'd begin scan. Firstly, the picture is larger than the typical face, and it's in color. So maybe I convert it to grayscale by averaging the colors out. I have my typical face, which is also grayscale. I make sure that the 2 are scaled so that the faces in the image roughly match the typical face in my that I've constructed from my data. And then I can begin trying to match my typical face at every position over here until I find the locations where my typical face matches the image. And so I'd get some notion of where in the image I can find the faces. When I do this, I'm scanning with my typical face. So what is the purpose of the scan? At each location, I place the typical face on top of a corresponding region of the image, and I found a match between my typical face and the region of the image beneath it. So how would I compute this match? An inner product, right? And so that's what I'd be computing. Express the region of the image behind that square as a vector. Your typical face is also a vector. The inner product is simply going to be computing component-wise products and then summing over the lot. And you know this is going to be maximum. When's it going to be maximum? When they're the same. So, and when they're close, you know, so you're going to get a map like this. You get a heat map. So there are those 3 regions where it found faces, and of the 3 of them, George apparently is most face-like. But then it also found a face where there was none on top, right? A ghost face. So that's a false alarm. Easy enough. But this wouldn't work all that well because, you know, as you can see, one little image, it's very clean. I begin to get ghosts. So this, and false alarms, you know, you can always find a false alarm. Sometimes you can express an appropriately pictured fishbowl with a face. So it's 2 true-false questions. All of you are done. Masa, what's the answer to the first question? What's the answer to the first question? True. And Kate, what about the second one? Right? For a normalized typical face, the scanning method of face detection is just checking on the length of the projection of the typical face on every same-sized patch of the image. And false positives occur because the dot product of a patch that looks nothing like a face can also be large, like the sink I showed in my intro lecture. So this business of detecting faces gets to be challenging, and sliding windows solve only the issue of location. What about scale? This used to be a very popular image for face detection experiments back in the day. There's Judy Batt's ad and poster, and it has 5 faces, each of them of a different size. So if all I gave you was this typical face, how would you find all 5 faces? I can scale this thing a bunch of different times. You know, just keep scaling my typical face up and down and then scan, or I can scale my image up and down and scan with my typical face, and both work, right? But then that doesn't capture everything. No, it doesn't capture head tilt, head orientation. And so if you want to do this, you'd have to go back and find every possible orientation of your typical face and scan, and every possible size. It's a painful thing. So this business, even the simple mechanism that I just showed you, can get challenging. And so this business of finding faces and images was a big deal for the longest time. There are, you know, many very complex methods. In the early 2000s, late 1990s, the best technique, CMU was the place you came to if you wanted to build a face detector. Henry Schneiderman had the most accurate systems in the world. And they worked okay. Actually, they worked quite nicely, considering all things considered. There was only one problem, that you could submit a picture to the algorithm and then go have tea and then have dinner, then go out on a date, and, you know, all the rest of those things, and come back next week and maybe you'd get an answer. So it took a lot of computation, a lot. And then something amazing happened. And this happened in the lab that I happened to be in. Paul Viola was a colleague of mine, and he and I didn't get along too well because he basically I'd set up a 500 processor cluster, and he used all of it for a system. So I mean, nah, I'm kidding. So he's a friend, but yeah. Yes. That's what they did. They had all kinds of things. And so what Paul Viola and Mike Jones did was they sent this notice out to the entire lab one fine day, and they said, just, you know, we're having a demo, please come to the auditorium. And so everybody walked into the auditorium, And as we walked in, they had a display showing the people walking in and tracking every single face in this display at 15 frames per second using a 400 megahertz processor. And this was 1,000 times, 10,000 times faster than what was being done at that time for the same accuracy. And the way they did it was using boosted cascaded classifiers. So boosting was like, and now that technique has 50,000 plus. Yeah, the two main papers have 50 or maybe 60,000 citations by now. It was huge. And it changed the game. Now, if you actually, you have face detectors on your camera, you can take pictures and it's going to mark up all the faces. And it happens in real time on the tiny device you have in your hand. You can thank these guys for it. If you use OpenCV, the Violagens algorithm for detecting faces is part of it. Of course, things have become much, much more accurate, much faster these days. But then the genesis is right here. So what is this all about? To get there, we first want to start even lower. What is this problem of classification? And this we are all familiar with. You're given a bunch of features for some data, like maybe for an entity, it says, this walks on two legs, it has no hair, and then the question is this a chimpanzee or a human being? So you're being asked to categorize the data in entity based on features, or it has long hair, it's 5 feet 6 inches tall, is it a man or a woman? Now these are features you're being asked to categorize. Or instead of having such unambiguous features, you could have something a little more ambiguous. It has something that matches an eye pattern with a score 0.5, a mouth pattern with a score 0.25, a nose pattern with score 0.1. Is this a face or is this not a face? Now all of these are different variants of classification. And classification, of course, can be done. You can have different kinds of classification. You can have multi-class classification. If I were classifying sounds, I'd have all the phonemes in the world, and given a little snippet of sound, I must find out which of these phonemes it is. I could be classifying amongst thousands of image categories, or even hundreds of thousands of image categories. In this case, we are performing multi-class classification because the number of potential classes is very large, or at least it's more than 2. If the number of classes is just down to 2, then you have binary classification. So here, man or woman, that's a binary classification. If I tell you that's only one of these 2. Or is this a face or is it not a face? That's also binary classification. But then there's something special about the second category of binary classification. And what would that be? Can anybody tell me what distinguishes face versus not a face from man versus woman? Yeah.
Not a face is really not a set of categories.
Not a face is an open set. It's unbounded. There are unlimited ways in which something can be not a face. Whereas in a man versus a woman, you can have, those are very distinctly stated categories. You know that it doesn't include a picture of a table or a picture of, your TV, right? So, whereas face versus not a face, you really have no idea. But that too is a binary classification problem. And in those cases, we have to come up with this notion of the negative. What is a negative, right? If I'm trying to build a pedestrian classifier, here are all possible negatives. Is this thing to the right a pedestrian or not? That thing to the left, is that a pedestrian or not? I have a reflection of a pedestrian in a glass. Is that a pedestrian or not? Defining this negative class becomes really challenging. So moving on. So detection is the problem of finding an entity, find a face in this image. But finding a face is actually, this is, detecting a specific category of object. Classification is all about finding the correct label. Here are all these labels. Which of these labels apply to my object, to my entity? And detection is actually a special instance of binary classification. In binary classification, you have only 2 classes, A or B. And when B is simply not A, then you have a detection problem. So this is what we're going to be dealing with in our face detection challenge. So this is what happens, right? When we are trying to scan faces can be many sizes. They can be They can occur anywhere in the image. So you'd be scanning the input for each face size at each location. You're going to be looking at each rectangle and classifying it as face or not face. And if it was classified as a face, then you detect a face. For this to work, you're looking at a large series of binary classification problems. And this binary classifier must be highly, highly, highly accurate. And you would be extremely happy if unhappy if your classifier began detecting calling trees, ceiling fans, and such like as faces. So you have to be precise. And so we're going to look at binary classification. What is the binary classification problem? In the abstract, I can think of it as some function, h, which takes an input x and outputs a +1 or a -1. +1 if it belongs to the class, it's detected. -1 if it is not. So, we're not specifying what the function h is. That, in fact, I'm going to leave open to you for the moment. What we will be looking at, what Viola and Jones Paul Viola and Mike Jones pulled off, was the use of a meta-classifier, a meta method. So how does this work? This is the boosting algorithm. It's all about ensembling method. It's an ensemble method that sequentially combines many binary classifiers to come up with a final complex, many simple binary classifiers to come up with a final complex binary classifier. And the simple binary classifiers are what we will call weak learners. And the complex binary one is what we'll call a strong learner. Now, the restriction is that the binary classifiers, weak learners, must be correct more than 50% of the time. Is it possible for a binary classifier to be wrong more than 50% of the time? Yes. Yes? Would you accept such a classifier? What would you do?
I mean, I would do the opposite of it.
And then what is accuracy?
The opposite of that accuracy is
So for a binary classifier, you literally can't go below 50%. That's the worst you can do. If you go below 50%, you just reverse the decisions of the classifier and you're better off than accepting the decisions of the classifier, right? So you just want things to be non-random. That's it. And the final classifier is going to be a combination of the decisions of the weak classifiers, and this somehow results in better classification than what is obtained using just a single classifier. So this was the boosting algorithm. So formally, we like to write math simply because it's the done thing in any machine learning class. So I'm going to give you math, but you can ignore it if you don't feel like it. So you're given a bunch of training instances, x, y. X is the input set of input features. Y is the +1 or -1 label that goes with it. You're speaking of binary classifiers, right? And then you're speaking of a meta classifier. So you'd be given a bunch of weak learners, h1, lowercase h1 through ht. Each of these can operate on the input x, and it outputs either a +1 or a -1, depending on whether it's a positive class by its guess or the negative class. And now let y be the true label. Now, if the classifier outputs a +1 and the actual label is also +1, then the product of the y and h of x is the product of two positive numbers. So it's going to be +1. Similarly, if the actual label is it's a negative class and the classifier calls it a negative class, then y is -1 and h of x is also -1. So the product is going to be +1 again. So anytime the classifier is correct, y times h of x is going to be +1. This I want you guys to remember because this notation comes back. Anytime the classifier is incorrect, y and h of x are going to have different signs. Y is the true label, h of x is the classifier output. The true label is +1, the classifier output is -1, the product is -1. The true label is -1, the classifier output is +1 again, the product is -1, right? And so we want a device. So we're given a bunch of these classifiers, these weak learners. I'm not specifying how the weak learners learned, although in the rest of the class, I'll give you one example of a weak learner because that's the simplest kind of binary classifier you can think of, and it still can generate very complex decisions. We are interested in devising this function f, which somehow combines all of these weak learners so that the outcome is actually better than any single one of the weak learners. So this function, I'm just going to succinctly represent it as f of x. How does one go about doing this? What we are doing here formally is boosting all of the weak classifiers. So we're using the individual weak learners, yes. I don't care. You can give me anything. Those are the weak learners, right? I'm focusing on the F, the meta classifier. I didn't know the DCT was a classifier, but that's okay. If you can, I don't care. That's the point, right? I'm interested in how we combine them. Okay. So what is the simplest thing you can do? If I give you a bunch of classifiers, what is the simplest mechanism you can think of for combining them? Vote. So explain.
The majority wins.
Majority wins, right? How would you formally write that down? If I sum them up. So basically, if I just summed, do I have chalk here? If all of my classifiers are hi of x, then if I perform this, and if this is my f of x, then if the majority of the classifiers think it's a positive class, what will the sign of the sum be? And if the majority think it's a negative class, negative, simple test, right? I can just sum them all up and look at the sign of the sum. And if the sign is positive, I call it a positive class. If the sign is negative, I call it a negative class. Easy. Can I improve on this?
You can weight each classifier by how accurate they are.
I can weight each classifier by how accurate they are. So things that generally produce random noise, you don't really want to trust them. Things that are always accurate, how much do you want to trust them? 100%. How do you define that? 1. So let me give you this example, right? I have 10 classifiers, 11 classifiers just for to make me happy. So I have H1 to H11. This is 100% accurate. And these are all accurate, 11% of the time, let's say, or some small, or less than 100% of the time. And this one calls it +1, all of them call it -1. If I just use this rule, what will happen?
The 11 bad classifiers will overtake
The 11 bad classifiers will overtake the one good classifier. But the one good classifier is always correct. So what weight must you give it? Thank you, right? I need to give this infinite weight. We have no reason to doubt this classifier. Simple principle, right? But more generally, here's what we're going to have, right? You can come up with a bunch of, so again, the simple classifiers can be arbitrarily simple. So if I'm trying to classify a human versus a chimpanzee, I can say if the arms are long, it's a chimpanzee. It's a simple classifier. It's right more often than it's wrong, but then you can find some chimpanzee, armed human beings as well. If you say if it's more than 5 feet 6 inches, it's human, but you find short people, and then who knows, somewhere in the jungle there might be a really tall chimpanzee. So if it lives in a house, it's a human. Chimpanzees have been brought up in houses, right? Every one of these classifiers is a simple classifier. It applies a simple rule. None of them is 100% right. If it lives in a zoo, the entity is a chimpanzee. Well, it doesn't work on some humans. Each of them is a reasonable rule, but makes many mistakes. So each rule has an intrinsic error rate. And we want to combine the predictions of these rules but not equally. Rules that are less accurate should be given lesser weight. So here is what we'd be doing. Corresponding to each rule, each of these rules is a box. It represents one of the classifiers, and every rule has with it a weight, an alpha, which gives you some notion of your confidence in the classifier. And now, just using this simple mechanism, if I'm just looking at the sign of this weighted sum, what am I really doing? H of x is either +1 or -1. So I'm summing all the classifiers whose output is +1. I'm summing the alphas for all the classifiers whose output is +1. I'm summing, and this is my score for the +1 class. I'm summing all the alphas for the classifiers whose output is -1, and this is the total score for the -1 class. I compare these two, whichever is higher, I choose that class. Make sense? Right, very simple. So this was a very simple weighted majority classifier, but what it's doing is boosting the simple classifiers. It's using other classifiers to boost the outcomes. Each of the classifiers is very simple. So the basic idea is that a weak learning algorithm that performs just slightly better than random can be boosted into an arbitrarily accurate, strong learner. And so this is a meta algorithm that poses no constraints on the form of the weak learner itself. Okay, any questions? No. So boosting is really a form of voting. It's a weighted majority vote, right? So you want to learn a large number of different classifiers to classify the data. And the key here is that they can be very simple. And you want to go with the majority. And intuition says that as the number of classifiers increases, the dependability of the majority vote increases. You'd expect things to follow this intuition. But we're going to be performing boosting by weighted majority. And so you take a weighted majority vote over all the classifiers. What's the key bit? The important question becomes, how do you determine these weights? Where do they come from, right? So if I were to ask any of you, how can it give me a mechanism to determine these weights? Johnny, suggest something. I have these classifiers here, right? How do I, somebody spoke on Zoom. Did someone speak on Zoom? We can't hear you, unfortunately, but yes. So how would you suggest a way of coming up with these weights? Yeah. 1 over the error rate. Kind of makes sense. But then what you're doing actually makes a lot of sense. But what are we doing here? We are treating every classifier independently, right?
Just like for a particular classifier to be given higher grades, like let's say that would be like medium for the difference to give like 1 it's in a half.
All of these are reasonable ways of coming up with weights. But what you're really doing is assigning a weight to each classifier without considering the other classifiers. Suppose I have a classifier which is right 80% of the time, but is always wrong on left-handed people. Then what is the next kind of classifier you want to give?
One that's good at left-handed.
Something that's good on left-handed people. So you want the weights assigned to these things. You want each classifier to make up for the mistakes that the other ones are making. And so the weights that must be assigned must be jointly optimized rather than just individually assigning weights to each of these classifiers. And that really was the challenge for boosting, right? How to optimize the classifiers and their weights. You want to optimize both the classifiers and the weights. And so the trivial solution is you train all the classifiers independently, compute each one of compute their weights independently. But no, the optimal solution is you want to train the classifiers jointly so that the data points that the first classifier makes mistakes on are captured by the second guy. And then you want to also optimize their weights jointly. So if you want to do this, how complex would that problem be? Aisha, any guess? Would it be simple? Would it be hard?
I think when you are doing them together,
It's going to be, can anybody give me some kind of an order of magnitude notion of the complexity. Isaiah, you answer everything.
It shouldn't be too hard.
Joint optimization, right? You want to say, you want to train, even if I have only 2 classifiers. Yes,
Every classifier
yes.
opens coefficient.
It's going to be, and it's combinatorial because you're going to be looking at, if you have n training data points, you're going to look at every possible way of partitioning the data and training classifiers and then finding the pair or finding the set of n that together give you the best, overall best classification accuracy, right? And so this is a combinatorial optimization problem. It doesn't have a solution. And this is where things stayed for the longest time. So Leslie Cabling, and who was the other guy who was from Harvard who won a Turing Award for his work on boosting. So he was actually earlier at CMU. Pretty much all of the guys who've done these great things have passed through CMU at some time. So they came up with this whole idea of boosting. Yeah.
So just joint optimization is like very difficult. It's just fully impossible.
It's as the training data set increases, it's going to be infeasible, right? So, and as the number of classifiers increases, it's going to be infeasible. So that's where things were stuck until we got this algorithm called Ada Boost. It's not named after Ada Lovelace. It's adaptive boosting. And the guys who invented this, Joab Freund is a friend of mine. When they came up with this, they were not thinking of boosting as an application at all. They were thinking of online learning algorithms and how to win at the racetracks or something like that. But they wrote a long paper on blah, 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 blah on online learning and an application to boosting. And the application to boosting was one small section of this very long paper. The paper is extremely highly cited. No one reads anything except that one section. So, because it became big. So the idea here is to keep adding classifiers incrementally to fix what the others missed. Our idea was that you want to train all of the classifiers jointly so that together they do the best job. But that's going to be impossible. So what you do is going to say, I'm going to train a classifier, and this classifier makes mistakes. So the next classifier is going to focus on the mistakes that this guy made. Then keep doing this, yeah.
So the complexity of the model would be like not exactly O(n) squared, but if there's like different of a particular.
It's 2 raised to n. It's not O(n) squared. Right? 2 raised to n. If I have 2 raised to n is the number of ways of partitioning it. Raised to k is the number of classifiers you're adding. So it's exponential. Right? So here's what we're going to do. So did the concept make sense so far? Questions? Yes. You keep retraining all the time. So we'll see how we will do this, right? So let's say I have these data, green data and red data. And so the color shows the class and the size of the dot shows you the importance of this training instance. Now, the way Joab Freund originally did it, he thought of selecting training instances from a set based on some weighting function. But this is the same as assigning weights to the training instances themselves. So I'm going to explain it in terms of assigning weights to training instances. So let's say these are all my training instances, the green and the red dots. And the size of the dots represents how important each training instance is. So initially, I've just got my dots, and everything is equally important. Then I'm going to train a very simple classifier. What's the simplest classifier I can train? Just a threshold. Everything to the left, I'm going to call pink. Everything to the right, I'm going to call green, right? And this guy is going to make a whole bunch of mistakes. What must the next classifier do? It's going to focus on these guys, correct? But can it ignore the ones that were correctly classified? Why not? Because it might be wrongly classifying the ones that the first one classified, and then it can mess things up. But we know the first one got those things right. So how do you increase the importance of these without losing those?
Previously active ones, classified ones, and decrease the ones which were like.
Perfect, right? That's exactly what I would do. I'd increase the weights assigned to the ones that have been misclassified and decrease the weights of the ones that were correctly classified. They're less important. Am I able to get this right? Then I train my second classifier on this one, maybe this guy. Right, and the second classifier now Make small mistakes, right? So this is the decision boundary that the combination of the two classifiers got. The first one called everything to the left of the first dotted line pink. The second one called everything to the bottom of the second dotted line pink. So the top right corner is being called green, but you know, these guys are all now. The second guy makes mistakes. The second guy has managed to misclassify things that the first guy got right. And so you don't really want to retain these mistakes. So what do you want to do? For the next classifier, you want to increase the importance of the ones that were misclassified by the second guy and decrease the importance of the ones that were correctly classified. And so now you change the weights all over again, right? Now you have a newly reweighted data set and you build a third classifier on these guys, right? And you can keep doing this. And eventually you're going to get a decision boundary of this kind. There's a hand raised on Zoom. Can somebody go on Zoom and find out what the question was? Is there a?
Yes, I have a question regarding to Adabus. So since decision is based on a majority vote, I was asking if we have a lot of weak learners. How do we know that we are not biased on weak learners alone?
You're not biasing on weak learners alone. Just wait till the end of the lecture and then let's go on. Let's see how this works, okay?
Thank you.
So did this make sense to you guys? This is the basic procedure we're going to be following. And so here is a little toy example. This is two clumps of data, blue dots and pink red dots. If I begin training a classifier using this technique, here is the final decision boundary that you actually end up learning. Now observe that each individual decision boundary that I chose was just a straight line, right? But when I combine them all, I got this pretty crazy decision boundary, which got the blues and the reds. Now there's some crazy stuff happening on the top right. Why is that?
No data there.
No data over there. There's no training data over there at all. So any odd rubbish can happen out there, right? That's part of the inductive bias of our classifier. But anyways, so the final strong learner has learned a very complex decision boundary while working off some very simple weak learners, where the weak learners were themselves just thresholds. It could have been anything else, but in this case, they're thresholds, right? And so look at that. The decision boundaries in areas with low density of training points are considered inconsequential, but the rest of it, I just nailed the decision boundaries, at least for my training data, and it's very complex. And you can get finer and finer. But there's something very interesting that happens, right? So if you look at this one here, let's go back to this example. Come on. Too many slides, right? So initially I have these data points. I'm going to have these data points have some innate difficulty in classifying, in building a classifier. But then I managed to build my first classifier, and I found that these are the guys that are misclassified. So the first classifier has already done most of the job. Is the job of the second classifier easier or harder? Easier or harder? How many think it's going to be easier? How many think it's going to be harder? And Puru doesn't have an opinion.
Same.
It will be the same. Here's the thing. The easy job has already been taken care of by the first classifier. Whatever remains are data that are harder to classify. So this guy has to work harder, right? So if you look at this, the first classifier makes a small number of mistakes. The next classifier is actually going to make a whole lot more mistakes, right? Because it's working on difficult data that were hard to classify to begin with. Otherwise, the first classifier would have got it. The third classifier is going to find data that neither the first classifier nor the second classifier were able to classify. So it is going to find data that are harder still to classify. And so what would you expect the accuracies of the classifiers, individual classifiers, to be like as you keep adding more classifiers? Will they keep increasing or they keep decreasing? Each classifier is going to be worse than the previous one. But what about the combined classifier? What do you expect would happen? It's going to increase. And so this is basically what you will see out here. So, sorry. This is the error of the nth weak learner on top. As you keep adding weak learners, the newer ones find it harder and harder to classify the remaining data, and the error heads towards 50%. But the strong learner, eventually it keeps getting, it begins to see easier and easier, begins to get better and better and better, and eventually the error is going to go to 0. So here is the crazy bit. This guy can go all the way down to 0, but the weak learners are going to be close to 50%. And so what you will actually find is that eventually you may get to a point where your strong learner is 100% correct on your training samples, but you can continue adding weak learners because you just got a bunch of weighted data and you can learn new classifiers. And so you had this very interesting phenomenon where you got to a point where you had 100% accuracy on the training data and you could keep adding weak learners. What would you call that? Can you say it aloud? So would you expect to see overfit over here? Yes or no? It doesn't happen. So this was the crazy bit that they found. They found that even after the strong learner's error goes to 0, that's one of the beauties of this technique. After the strong learner error goes to 0, if you keep adding weak learners, the generalization keeps improving. So what seems to be happening over here is that there's some notion of a boundary. How far away? Remember, you're looking at the weighted sum of the classifiers. And so what is the smallest value of this weighted sum? That's how far away you are from the decision boundary. And this smallest value keeps increasing as you keep adding weak learners even after the strong error goes to 0, which means you're increasing the margin. You're going farther and further away from the boundary. And so you get making more room for test data. So this was one of the proven beauties of this algorithm. Very nice. So again, summary, no relation to Ada Lovelace. It's adaptive boosting, adaptively selects weak learners, not 20, I think it's more, 24K citations from just one paper by your Freund or more. So he and Rob Shapiro got the Gödel Award for this work. And yeah. So anyway, we will go through the algorithm in some detail, see how it works. When the first time you see the algorithm, you're likely to just get confused and you would likely to wonder where the heck it came from. So then you're likely to go and read the paper, at which point you're likely to get head spins. And if you're weak-minded, you're likely to get drunk. But it's actually quite easy to intuit where this comes about from. Yes.
Does it matter if the weak learners are trained deterministically, like from probability?
It doesn't really matter. I mean, the general meta principle still holds. Right? Okay. Karan, do you want to answer if the first statement is true? Okay. Akanksha, is the second statement true? False. Johnny, what about the third one? And frame the fourth. So AdaBoost allows for the use of several simple weak classifiers to build a strong classifier. That's a weighted majority vote over the weak classifiers. It's not prone to overfitting, amazingly enough, right? This is a shocker. You would never have believed this of any algorithm, that I can throw in a million more parameters and it's only going to get better. And it does overfit, but then it's much more robust to overfitting than standard algorithms. It's greedy. Joint optimization was quite impossible. So what we did was just do it one step at a time. And then it trains all the classifiers independently. No, it doesn't, because each classifier is fixing the errors that the others made. So what does the algorithm look like? Like this. Can you parse it? I cannot, right? So I'm going to explain this algorithm. And once I'm done explaining it, then maybe you can write it on your own without looking at the slide. So let's see how this goes. Let's go through this one step at a time. I'm going to start off by showing using some example data. I'm working with examples because, makes sense, right? So let's say I have a bunch of images and I'm building a face detector. So I have a bunch of positive images that those are actually faces. I have a bunch of negative images, and I'm going to learn some eigenfaces. So when I learn eigenfaces, I know that faces are better represented using eigenfaces and non-faces are not. So the weights with which the eigenfaces are combined to construct the face and the error between the construction and the actual data. These could be my features, right? And I would expect that the weights would have a different patterns for faces and non-faces, and the error is going to be larger for non-faces. That's my expectation. So these can be my features. And so my data is going to be something like this. I have a bunch of 8 training data instances, 4 faces, 4 non-faces. I have 2 features. Think of them as, maybe weight and error or whatever. It doesn't really matter, 2 features. And then I have the class label, +1 for the faces and -1 for the non-faces. Any questions about where this comes from? Okay. First step. The very first step is this picture here. Remember, I'm going to assign equal importance to all of my training data. Now, there are 2 ways of dealing with assigning with importance. In the one case, I can actually assign a weight to the instance and factor the weight into error computation and such like. In the other case, I can sample data points according to these weights. And so both of them are equivalent. And so you can also think of this as sampling my training data instances according to this distribution where I have assigned the same weight to every training data instance. And now I'm going to build my first classifier using the training data instance. Now the sum of these weights is going to be 1. Keep that in mind, okay? So that's like saying I have 1/8 for all of my training data instances because I have 8 training data instances. And now I'm going to try to build a weak classifier using my training data. My weak classifier must use the distribution dt, which is the set of weights. So again, there are 2 ways of thinking about it, that I've sampled the data according to the distribution, or that I've assigned weights to the data instances. I'm going to use the assigned weights interpretation, but if you did it the other way, it would be just as right, okay? So here are my 8 data instances. So let me build the simplest classifier I can build. What's the simplest classifier I can build? A threshold function, correct? So I'm going to be greedy. I don't need to be greedy. I could have just picked any odd classifier. So long as it was better than random, the whole thing should work. But I'll just be greedy over here. So to be greedy, here's what happens. And I'm being greedy just to explain to you how the error business works, okay? So let's say I decide to build stumps. Stumps are just thresholds. So I'm going to build a stump based on feature E1. And so here are my 8 training data instances arranged according to increasing value of E1. And their weights are written below the instances. Now, a threshold can have 2 outcomes. It can either say everything to the right is a face and everything to the left is not a face, or it can say everything to the right is not a face and everything to the left is a face. 2 different ways of looking at it, right? So let's say I apply a threshold over there. The values for the thresholds are between training data instances, right? So let's say if I have my threshold all the way to the left, it's a useless classifier. It's just calling everything one class. So if I have my threshold out here and I call everything to the right a face, then I'm making 1, 2, 3 errors, right? And so the total error is 3/8. It's the sum of the weights of the data instances that I have misclassified. If I call everything to the left a face, then what happens? I'm going to make mistakes. Would it be 5/8? Yeah. So if I call everything to the left a face, these 4 blues and this one black are all going to be misclassified. So I'm going to have error of 5/8. So which of the 2 would you choose?
3/8.
So 3/8, calling everything to the right a face, right? But I don't stop here. Then I go forward. So that sign is 5/8, right? On the other hand, if I say everything to the right is a face, then those three crossed out guys are wrong. So the total error is 3/8. And so I pick the best one. I'm going to call everything to the right a face for this threshold. Then I can take a step forward and repeat the same arithmetic. And I find that if I call everything to the right of face, my error is 2/8. And then I can try the next threshold and the next threshold and the next threshold. And eventually I'm going to find that if I base my classifier based only on, build my classifier based only on E1, then the best classifier applies a threshold between instances G and B, a threshold of about whatever that value might be, right? 0.45. And in that case, I'm going to make just one mistake. The error is 1/8, right? So the class, this is just the equation which says that sign times weight should be greater than threshold, because I'm just assigning a sign. This is, when you write math, the simplest concepts become really ugly. And so that's what happens in the boxes where it's ugly, but the pictures should tell you the story, right? And so now that's my best classifier using E1. Is there a better classifier using E2? I can try. I can now pick up E2, arrange my data instances according to increasing value of E2, scan through the thresholds as before, right? And I find that my best threshold is right here when E2 is, say, 0. And if I call everything to the left of face, I'm making two errors. The total weight of the error is 2/8. So of the two, this one's better, right? So this was my greedy way of picking a classifier. Now, what is the total error of this classifier? 1/8 is the total weight of all the training instances that are misclassified. And so basically, this was my best stump, right? Now, what is the error? So that was training this classifier, this first step. That was training this first step. The second step looks really ugly, right? What is that second step doing? Again, this is the old adage that math can make you if you really want to confuse people, write math. But here is what it is. If we said, what was y times h of x? 1 if it's correct and -1 if it's not, right? So what is 1 minus x? It's either 0 if it's correct, 2 if it's not, right? So what is half of this? 0 if it's correct, 1 if it's not, right? It's a count of error. And so that funky formula over there is just using this formula to determine if that thing has been misclassified, and it's adding the weights of all the misclassified instances, and that is the total error. Somebody poke Bode. He's falling asleep. Yes, okay. So that step makes sense? Okay. So now we know the error of the classifier. Okay. Next, once I have the error for the classifier, this is, do I have a slide on this? That's this guy. You're counting the weights of the misclassified instances. That's actually, we've already got that. It's a funky formula. We're just telling you that this classifier made a total error of 1/8. Okay. The next thing we want to do, we have a classifier. You want to assign a weight to the classifier. What are the rules you want to assign? Firstly, assuming that you're being sensible, then you don't even have to assume that you're being sensible. So if the error is 50%, how much weight do you want to give this classifier? It's a random classifier. You don't want to use it, right? If the error is 0, what is the weight you want to give it? If the error is 1, what's the weight you want to give it? It's always wrong. What's the weight you want to give it? Negative infinity, right? Flip it, and then I believe it 100% of the time. So can you give me a function of epsilon, of error? Is there an eraser here? Why do the erasers disappear? So this we said is the error, right? D of. That was the error. Now I want a function which has this property, which is when E is 0, when E is 0.5, f of E equals 0. This is what we wanted, right? When E is 1, what did we want f of E to be? Infinity, right? And when E is
Negative.
0, actually no, E is 0, you want f of E to be infinity. And when E is 1, you want f of E to be minus infinity. Can you give me a function which has this property? Anyone? Think.
Something is about a lot.
Something using a? Okay, keep talking. So log. Okay, go ahead, Isaiah. Karan, you guys are on the right track, right? What would it be? Log of what? I just write ln because I'm lazy, it doesn't matter. Log of what? If it's log of E, would that work?
1 minus.
Log 1 minus somebody else. Give me a negative. They can't take the log of a negative number, right? Someone give me an answer. This is not a trick question. What? 1 over E. Let's try that. That's just minus log E, right? Does that work? No. Somebody else? Let's focus on this. When E is 0.5, f of E is 0, okay? I'm going to go with the thing that the log makes sense. Only logs go after infinity. So what would work? What must the argument of the log be for this to become 0? No, what log of what is 0? Log of 1 is 0, right? So what must the argument of the log be for this to be 0? It's got to be 1, right? Somehow I have to squeeze that 1 out of 0.5. How can I do that? Raise to 0, but then if I raise to go ahead, what? So the E over 0.5. Okay, let's try this. Does that work for this guy? It doesn't work, right? So, but maybe you're getting close. What can it be? So here is the crazy thing, right? So here E and 1 minus E are both identical, right? So if I just did a log of E minus log of 1 minus E, that's going to give me a 0. Yeah, correct. What do I get when E is 0? This is going to become, if E is 0, this is going to become infinity, correct? And what is this going to become? 0, right? And if E is 1, this becomes 0 and this becomes minus infinity. Do I have the property I want? Yes, no, right? And so that's basically what we do, right? There's now, because you want to be mathy, for some reason there's a 0.5 that comes out for reasons of optimality, but it's just log of 1 minus epsilon over epsilon. So when E is 0, that's going to be, actually I think it's the other way, right? To get it right.
Yeah.
And then you can see that it's half of log of 1 minus epsilon over epsilon. It's not hard to figure out where that formula comes from. It's hard to figure out where the half comes from, some constant, but within that constant, the rest of it is fairly intuitive and straightforward. That makes sense to everybody? And so that's basically what we will do. We're going to assign alpha equals, okay, go ahead, here's a form. Someone's going to answer the question. Okay, easy. Someone tell me all three answers. True, true, and false. Is that right? Because the way it assigns weight 0 to a perfectly random classifier, infinite weight for a perfectly correct classifier, and we assign minus infinity weight, right? So beautiful. We got this all. And so for this classifier, it just turns out that the weight is 0.97 in my example. Okay, that's done. What is the next step?
Updating the weights for the points.
I want to update the weights for the points. And what do I want to do? How do I want to update it? Anybody? How would I update it? What does intuition tell you?
Simplification has to stay normalized.
Yeah, but that, just in terms of updating, would you be increasing or decreasing the weights of instances that were correctly classified?
Decreasing the weights.
Decreasing the weights of instances that were correctly classified. What about instances that were incorrectly classified? Increase it. And the classifier's difficulties, the difficulty faced by the classifier is the same in both cases, right? So the factor by which you decrease the weights of correctly classified instances is going to be the inverse of the factor by which you increase the weight of the incorrectly classified instances. And what would be a good thing, right? Can anybody tell me? So let's see. Let's use our logic again. If my classifier is 100% right? How important are the classifiers that it got, instances it got wrong? Yeah, the instances that it got wrong. Very, very important, right? How important? Infinitely wrong, infinite, right? And what about the instances it got right? Those were easy. Now they're done, right? So what would be a good weight, just given this? Go back to the same thing that we just saw, right? It's going to be, I can literally just say if my classifier was always right, then any instance that it got wrong. So let's think of the situation where E is 0 or E tends to 0. For correct classifiers, correctly classified instances, I want to make this maybe so D of E, right? For correctly classified instances, right? And for incorrectly classified instances, maybe it's D over 1 minus E, right? So something of this kind. So you can actually work your way through the arithmetic, and here's what you actually get. This is this guy, E raised to minus alpha YH. Y times H is simply telling you whether it was correctly classified or not, right? So basically it's either E raised to plus alpha or E raised to minus alpha, which is basically just E over 1 minus E over E, correct? And so for correctly classified instances, it's going to be multiplied by E over 1 minus E. For incorrectly classified instances, it's going to be multiplied by 1 minus E over E. Does that make sense? Right? So yeah. So this, okay, my arithmetic, I've written some, let me erase this. Let me just give you something let's look at the extreme case where I have an infinitely accurate classifier. So if I have an infinitely accurate classifier, then E is 0, right? If I have a misclassified instance, what do I want the weight to be? Infinite, right? So that's going to be proportional to 1 over E. This is my proportionality thing, right? And if I have a correctly classified instance, it's going to be proportional to E, right? So basically the one that works out both ways is simply going to be the same as the alpha. It's going to be 1 minus E over E. And if it's random, if the classifier is perfectly random, then do I change the weights of anything? It doesn't matter whether it was correctly classified or not. E was 0.5, so that doesn't work over here, right? Let's look at the two extreme cases. If I have a random classifier, I don't want to change the weights of my instances. If I have a perfect classifier, anything that is misclassified gets infinite weight. Everything that's correctly classified is dismissed. What works in both cases? So that's simply going to be 1 minus E over E. For a random classifier, this is just 1, right? It doesn't matter whether it's, so you're going to have one of these guys. So for a random classifier, both are the same, no weights change. For an infinitely correct, for a perfect classifier, where E is 0, then this is what would apply to correctly classified instances, right? And this is what would apply to incorrectly classified instances. Does that make sense? Just the intuition of it, looking at it. Does that make sense? You can work your way through it. You don't even have to think very hard. If you look at the math, it looks much uglier than it should be. That's because, you know, if you want to write a formula, this makes more sense, right? So you want to write the weights in terms of the alphas. And so that's basically what we're going to do. We're going to scale our weights by either 1 minus E over E or E over 1 minus E, depending on whether it was correctly classified or incorrectly classified by the latest classifier. That's going to give me a bunch of things that no longer sum to 1. So I must, I'll just change the weights, right? But then, hey, wait, there's a poll just for the joy of it. Yes. Okay. Is the first statement true or false? Second one, third,
False.
right? So if the classifier is perfectly random, you don't change the weights of the instances. That's basically what you want to do. If it's perfectly correct, you scale down the importance of the correct classifiers to correctly classified instances to 0, and incorrectly classified instances are scaled up to infinity. And this is logic. This is how you would think your way through it if you are thinking logically about the problem and not math. And the math follows the logic, right? It's not hard to figure your way out. And once you sort of figure out how this happens, then you can go ahead and devise your own algorithms, which basically follow the same principles. And if you do, odds are that whatever algorithm you come up with, it will turn out that someone somewhere has actually written a paper about it and proved theorems about it. Right? Because it makes sense. And so that's what we have. And then finally, you want to normalize the whole thing to sum to 1. And when you do that, you find that there's this one measurable instance, A, which got misclassified, whose weight has gone up from 1 over 8 to 0.48, and all the other ones have had their weights go up, right? And so now I can have, so these are my new weights. And then I have done this last step. I can go back and train my next weight classifier. I have the data again, but now I have new weights for those. And then when I begin scanning through the thresholds for each feature, I'm going to get a different error because the weights are going to be different for the different instances. And so I'd scan through and find the threshold with the best error, right? And in this case, it's going to find that for E1, it's this one. For E2, it's this one. I could be greedy. Again, I don't need to be greedy. This is just me being greedy, right? But you could pick any weak learner, so long as it was not the same as the previous one, or it can even be the same as the previous one. Things will keep changing, right? And so you'd get a new classifier, and you can compute the error for the new classifier. The error is just the error that you got while you were scanning through the thresholds. And then you can just plug in the formula that we just saw, for both the alpha and the reweighting of the instances. And then you updated the whole process. You've got the weight for the classifier, you've got the new weights for all the instances, you can normalize those, and you get reweighted instances, and so on and so forth. This just goes on, right? And you might find that you keep picking the same features over and over again. So here in this case, I have only 2 features. So you would expect that if I've built a classifier, which is a threshold on one feature, that feature is done. I'm not going to come back. But that's not the case, because every time you update the meta classifier, the data have been reweighted. And so the same feature can get rechosen. And in fact, it can be rechosen many times in a row. It's to give you your final meta classifier. And so in this, in the example that I just showed, if you go through the slides, you'll find that both of the first 2 classifiers are just based on feature E1. This can happen. But the important thing is, eventually, if you look at the ensemble of all the classifiers, you'll get a very tight decision boundary around the data. And then you get something very, very much more interesting. Besides the fact that you could take these completely crappy classifiers, just thresholds, and then boost them into something that can be 100% accurate on your training data, and keep improving on the training data. There you find, in the case of the threshold-based classifiers, you get something interesting. So let's say the features I chose for my sequence of classifiers were feature F1, F1, F2, F1, F2, F2, and so on. And then I had the corresponding weights, because each classifier has its own weight. Then this actually tells me the importance of the features. If I sum up the weights of all the classifiers that chose F2, that's going to tell me how important F2 was in the entire decision process. If I sum up the weights of all the classifiers that chose F1, that's going to tell me how important F1 was for the whole decision process. And so it gives you a feature selection strategy as well in the process, a feature importance strategy, right? So again, you're not required to go with the best classifier so far. I could have chosen any odd classifier. In my case, I could have chosen a classifier that was based on E2. So long as it's it's right more than 50% of the time, which it will be. In fact, it doesn't even have to be right more than 50% of the time, so long as you're willing to live with negative weights. It's just that we don't like negative weights. So it's better to flip your classifier and live with positive weights, right? So, and then you can continue to add classifiers even after you get 100% classification of the training data, because the weights keep changing. And adding new classifiers beyond where you have 100% accuracy on the training data is actually a good thing to do. Now, what is the worst thing that you can do for AdaBoost? Random classifiers, no. Random classifiers are not going to kill you. If you ever get a classifier that's 100% perfect on your training data, you are done, right? If the weak learner is 100% perfect, there's nothing more you can do. All the weights become infinity or 0, and then you're screwed, right? So here's a crazy situation where you can train an arbitrarily strong meta learner which generalizes greatly, provided all of the component classifiers are not very good. Once the component classifiers begin to get very good, then this thing is going to fall apart because the weights go wonky. That makes sense? Yeah. And so, and the final classifier, you're going to have a bunch of weak learners, each with its own weight. You just apply a weighted sum and then look at the sum for the output. So that's your final classifier. The output is 1 if the total weight of all the weak learners is greater than the total weight that classified as 1 is greater than the total weight of all the learners that classified as -1. So this was boosting, AdaBoost. This it's the basis of the Wheeler-Jones algorithm, the most thing that actually revolutionized computer vision, to be honest. Current methods use, CNNs, SVMs, various other things. OpenCV implements this, and the nice thing with AdaBoost is that it's really trivial to write. And Yoav, the guy who came up with this AdaBoost classifier algorithm, he and Rob Shapir, these guys tried very hard to outdo themselves afterwards. It turned out they had peaked. They came up with various algorithms which sort of improved under various conditions. But this algorithm is so beautiful and so intuitive and simple that it's really hard to beat this. I mean, you can come up with ways of thinking above and beyond what we just saw. How would I expand it to a multi-class classifier? Things like that. But still, I think it sort of got to a sweet spot in the simplicity performance scale. And we'll see in the next class how we can use this for detecting faces very trivially, and how people could run this at 15 frames per second on a small processor 30 years ago. Okay. Questions? Okay. I may not be here in the next class, in which case some designated instructor, possibly one of our PhD students, is going to come and conduct the class in my place. Be kind to him. He has not taught before. Yes.
Your from your kind of experience, which learners tend to work the best, or is it decision stuff such?
So people have tried all sorts of things. They actually have boosted decision trees are the thing. And boosted decision trees actually tend to be possibly the best classifiers around. And many problems until neural networks came along and were trained on massive amounts of data. Boosted decision trees were it. The idea, of course, the point is the idea of boosting is so pretty that, after seeing these things, you feel bad about going back and training a dumb neural network. Questions? No? Thank you. In class.